So we just wrapped up our introductory. It's actually called what we call as a teacher a hook activity, where you hook you in to the concept through the density lab. We use the density lab to begin exploring the idea that the periodic table is the most magnificent model out there, because it reveals a lot about not only all the elements that exist and have been discovered, but it also reveals many layers, such as the atomic structure itself. There's characteristics that you can't see necessarily directly on the periodic table, but if you know how to read it, you implicitly know it as well. Okay, so this was our step in, our gateway activity into the periodic table and electron study for unit 2. You guys should have turned in your density lab CER. I'm saying this for the folks that are listening at home. Density lab CER can be revised with comments after initial grading. Okay. And of course, you have your unit 2 notes and workbook downloaded, and you're expected to look on my agenda every single day and do the workbook problems, because that's 5% of your grade. All right. And now I've asked you to, 1, complete this density section just to make sure you do know how to calculate density. And 2, look at your personal periodic table that you have a copy of and start looking at what you know, any other patterns that you see, or any other previous knowledge that you already know about it outside of the lab activity that we did. 8309. So, out of curiosity, we already know the density equation. You guys know the 2 units. And by the way, any unit that consists of 2 units, right? So like grams per milliliter, grams per centimeter cubed, 4 quarters per $1, $1 per 4 quarters. Anytime you have a relationship between 2 different units, that could turn into a conversion factor. That's a math tool now, right? So just a little reminder, unit conversions never go away, ever. Okay. So a teacher performing a demonstration finds that a piece of cork, okay, displaces 25.5 milliliters of water. So here, of course, we are referencing our water displacement method for awkwardly shaped things, right? This water displacement method for awkwardly shaped solids that length times width times height doesn't do justice for, right? The piece of cork has a mass of 7.7 grams. What is the density? I am hoping to the good everything above, all right, that you guys are able to do this basic math. You set up mass over volume. So 7.7 grams over 25.5 milliliters. And what do you guys get for the value itself? Who did the math? No one did put this in the calculator. Not a single human. 0. What? 30? 0.30 grams per milliliter. What is the uncertain digit? As far as precision goes, the uncertain digit is always, for a measured or calculated value, it's always the what? The uncertain digit is always the what? Yes, Mika. The last digit, okay? On a measured scale, right, your mass and your milliliters would be the last digit for each of those. That's your raw data calculated, put into a formula to give you your completed finished data, right? There's raw information, and then there's the valuable finished information that we get from the raw information, usually via an equation. Yes. From this point on, honors, you like all honors work to be finished in stick things, correct? From this point on, honors would want to keep that in mind. Yes, I tend to be explicit to honors when I really am grading for sig figs. Yes. So, round to the hundredths, please. So, here we're seeing a conflict between honors and prep. So, from a general standpoint, that last one. I see. Okay, we're seeing a conflict between honors and prep right now. How am I going to explain this? I think it would be better actually to stop at 0.3. Because that way it's consistent with the digit placement of the raw data uncertain digit. And then for honors, you would technically have 3 sig figs. Ooh. Yeah, this is where honors and prep just need to think differently, okay? When I talk about uncertain digit, I want you just to think in the general mindset, final measured digit placeholder. I will tell you, honors, when you need to think in terms of sig figs. You will see there are contradictions at times, like just now, where sig figs for honors would tell you you need 3 of them for this problem, for this mathematical equation. But for generally speaking, all your measured values aren't that precise, right? So yeah, here we're seeing a contradiction between honors and sig figs. Honor sig figs and general prep uncertainty and precision understanding. Yes.
Sig figs would make us, you only need 2 because even when it's multiplying, it's what everyone has to understand. Sig figs, that's everything else we need.
Right. So honors would turn this into to have 2 sig figs, SF. Honors would turn this into 0.30 grams per milliliter. But precision wise, uncertain digit wise, measured calculated value, it doesn't make sense that we suddenly gain certainty in the 100th place.
No, I know that. But, that's 0.30. Isn't that 3 sig figs?
That's 2 sig figs because it's the 0 after a non-zero number and a decimal. But the 0 before that is just a placeholder.
0 point address, just placeholder.
So this is non-significant and these 2 are significant. Mm-hmm. Yep. So honors, that's the little detour. Yeah. Okay. Good. Ooh, yay. Okay, so that's kind of the end of that. We're wrapping up that Density Lab CER. Unit 1 reminder, right? Your ability to do scientific notation, unit conversion, honors, sig figs, and everybody in general, right? Precision in general. And now we're just taking a step back from all that like very tedious work, and we're going back to the big idea. How does the periodic table tell us information about the elements out there in the world? What can we know from the periodic table? And we already know one thing, right? We already know one principle. Could you tell me that principle, Carlos? What was the principle that we explored in the lab?
That it's organized.
That, and why do we care if it's organized? You wrote about it in your reasoning. It's in the top of your packet. I had you highlight it, annotate it. Why do we care that it's organized? What's the big idea? Bryce, do you happen to know? Excellent, excellent. It's organized in such a way that we can predict the properties of elements. What's one example of how we use that to advance? What's one example of its organization? What's one example of its organization, Liam?
Carbon family with uranium.
Too specific. You're on the right track, but too specific. What's one example of the organization of the periodic table? Yes. Columns, finish it off, Jose.
They share the same properties.
Yes, elements in the same column share similar properties. That's one example of how it's organized to allow you to predict information. Because we can say, well, down a column, I'm going to have some type of pattern or trend along a certain property, okay, for those respective elements in the same column, in the same family, right? So this is the big question that we're going to be addressing for the next couple days, right? This is the real question of our unit. That density lab was just to get you in the foot in the door. This is the real question of our unit. How does the organization of the periodic table allow us to predict properties? And we already know that the periodic table is organized by increasing atomic number, right? Originally, it was organized by increasing atomic mass, but we noticed that there were some inconsistencies. And mass is kind of subjective, like it really is. Like it just changes too much from material to material. But a proton number is 1, it's a whole number, it's a set number, and it's just real nice. It's an upwards count of 1. No decimals involved, no complications, none of that, okay? And you can sit by Lachlan, and here's printable if you want it. So we also know that it's organized by rows and columns, right? and I definitely misspelled columns, slash families slash groups. Okay. And we also, by the way, called rows periods. Notice the periodic table, the road table. Okay. The periodic table is literally the road table. Like I have rows in a table, which I don't know many tables that don't have rows, but you know. Um, so we have many ways that we layer organization. So I'm going to be for the next couple days starting to tackle multiple layers of the onion of how the periodic table is organized to reveal things. Those layers of organization overlap, but are distinct at the same time. So you need to know as we progress in unpeeling away the information of the periodic table, you need to be mindful of, does this organization like strictly overlap with another set of organization hidden within the periodic table, or are they kind of just two coexisting organizations, two coexisting layers of information? Okay, so keep that in mind. The first layer I'm going to give you is how is the organization of the periodic table, okay, tell us about the type of general categories of elements we have, because we have like what 120 or 118 elements, and we could name them all individually, but then we can group those elements as a general type. And the general type is metal, non-metal, and metalloids. Metal, non-metal, and metalloids. So metals, all right? These elements, they consist or make up 80% of the known elements in the universe. Of all elements. So you'll see in red, see that in red right here? These are the metals. Now notice hydrogen is awkward. Hydrogen is a non-metal that's placed on a metal side in the periodic table. If you look at your periodic table, it's placed right on the side of a metal. There's a reason for that. Hydrogen, you just kind of got to remember that hydrogen is like awkward and it's like own, it's like doesn't follow any specific trend. It kind of breaks all the rules all the time. And it like dibbles and dabbles in various rules. And then it makes its own. Yeah. It's like older siblings when they play a game with their younger sibling. You dibble and dabble in some of the rules to be recognizable as a game, and then you change the rules so you win. That's what I did. So metals tend to be dense as solids. And they're also just in general usually solids at room temp. RT stands for room temp, room temperature. Right now, right here, solid. Metal, iPad, computer. Okay, my phone, solid. Okay, a pan. Thank the Lord, solid. Right? You don't want to cook in liquid pan. That'd be some gross omelet. Okay. They tend to be what we call lustrous or shiny. Right? Like Moana the lobster, shiny, right? No, okay. They are very good conductors of heat and electricity, which again is why you cook in a metal pan, not an oxygen pan. You don't cook in a helium pan, all right? You aren't gonna get really anything out of that except for death and gaseous poisoning. So we cook in metal pans because they transfer heat. You already know this. Metal transfers heat very well. It's why you burn yourself on your curling irons, on your, I don't know, power tools. I don't know what you guys use, power tools, on your, even your charger when it gets hot, or your like hydro flask if you leave it out in the sun too long, right? And on the other hand, non-metals, which is, by the way, the yellow region is the non-metals. So here is the red region. And this is the yellow region. Is non-metals, all right? And these are the rest of the elements for the most part. And they are usually gas or liquid at room temp. So oxygen, non-metal, gas, you breathe it in. Hydrogen, non-metal, also gas, okay? Carbon, actually carbon's kind of unique. It's actually an example of when a non-metal is a solid. Okay, when it is a solid, it tends to be brittle. So carbon is a good example of a non-metal that can be solid at room temp, but it tends to be brittle, which is a good indicator that it's a non-metal solid, not a metal solid. Metal solids, they're not really brittle. They're dense, they're chunky, okay? They're pretty firm. Carbon, graphite, right? Yes, Mika. Yes, mercury. Mercury. Mercury is liquid. Mercury is really cool because it's a really dense liquid. So when you hold the liquid in a container, not you hold the liquid. When you put the liquid in a container, it actually is heavy. You actually feel the weight of it. Yeah. Dad, tends to be brittle. Thank you. Tends to be brittle. Okay. Non-metals are very bad conductors of heat and electricity. Okay. Chemically wise, so far I've described everything as a physical feature. This is so far I've described pretty much all physical nature of these general big categories of elements. Chemically wise, you should know this about metals. Chemically, okay, metals lose electrons. And what they do is they like to become cation. They like to become more positive, some way or another. On the other hand, non-metals, from a chemical perspective, they like to gain or share electrons. So they either take on an anion position or at least more negative. Maybe they can't get fully negative, but they can get partially negative. That will make sense in a couple weeks. Okay. And then we have this weird category known as metalloids, and that is in purple. The purple stair step is metalloids. Right here, these metals right here are metalloids. Okay. And these are interesting because they have both metal and non-metal characteristics or properties. What are you looking at? Cations. Mm-hmm. I can erase that and make it better. Oh, sorry. Sometimes I shake and it translates to the pen. Metals. Okay. Cations. Okay. So metalloids have both metal and non-metal properties. And what we say is that they tend to look like a metal. They get the looks of a metal. Interesting. Look like. Interesting. Cannot spell the word like. Look like metal. But they tend to chemically behave like a non-metal. So they will gain or share electrons, usually. Metalloids are mid-conductors. They're what we call semiconductors. They're semi. They're not great at it, but they can. They're like the B team of conductors, okay? Semiconductors of heat and electricity. Okay? Semiconductors of heat and electricity. Okay. And could you cut out about 16 of them, just in case someone messes up? All right. So there's another kind of special category within metals, and that's called transition metals. Okay. These transition metals are a category, a subcategory. I'll say subcategory within metals. These are weird. Okay. These are really, really weird. Transition metals tend to be super dense. These tend to be super dense. No, what actually, you know what? I'm thinking of the wrong one. Erase. Don't say that. Sorry, I'm thinking of the wrong category of elements. What they do is they tend to be colorful. And their colors can be used to be an identification property. Okay, which is unique because honestly, not always colors isn't always the most reliable because lots of things are just like silver and you're just like, oh, okay. But transition metals usually are fluorescent almost like bright yellow. I'll get out one of them right now in the back. Hold on. Let me pause. So cupric sulfate, for those of you at home, look at it, it's so pretty. Okay, copper, cupric copper, equivalent name, transition metal, bright blue. Okay. Next, iron. Iron, it's a Mars color. Iron is Fe on the transition metal periodic table. Folks at home, here's an example of a non-metal solid. This is sulfur, very brittle, very powdery, very exciting. Okay, so that's kind of an overview of some of the main categories of metals. Transition metals, we're gonna get into later. Like this is a really unique section of elements. Especially when it comes to bonding. Like it's really special when bonding. So we're gonna get into it later. Okay, by later I mean like in 3 days. Okay. Also, I think I did a bad thing. You're not technically supposed to snack on anything when you're holding chemicals, but I'm fine. Okay, so now I'm gonna get into the next layer of the onion, next layer of the periodic table organization. Okay, and I want to quickly go over unique columns, unique families. Okay, so what we have here is the first family is the alkali family. Okay, column 1 or 1A. And note something, it does not include hydrogen, even though hydrogen, okay, is placed, all right, in the same column. It does not include hydrogen. Alkalines, all right, are right afterwards, column 2, 2A, okay? They're very similar. They're very similar, okay? Similar to alkali, but differ in reactivity. Basically how it bonds, or differs in the way that it bonds, activity. Okay? Halogens, all the way on the other side of the periodic table, okay, are very unique in bonding. They, when bonding, are desperate for one more electron. Because guess what? They're super close to a noble gas. They're 1 electron away from a noble gas, right? That's also kind of unique about them is when they're alone, when halogens aren't bonded, okay, they tend to bond to themselves, right? So a metal can just be like a plain mercury atom. It's like fine, chilling by itself. Chlorine can't handle that. Chlorine has to be chlorine 2, not plain chlorine. It cannot handle just being chlorine by itself. It either has to be a charged chlorine to exist or chlorine 2, chlorine attached to itself, but it cannot just be chlorine. It can't handle it. And then noble gases, of course, we know are really unique because everyone wants to be like them. Okay, and we do put helium as a special noble gas. And I'll explain why we consider it special in a little bit. So we're going to get just a little bit more into some of the characteristics, and then we're going to go into an activity, and that will be the rest of our day. Okay. And hopefully, if you were absent any days prior, you know where to find my uploaded lecture videos to watch and take notes, and you've been doing that and looking at the agenda. Make eye contact with me. Okay. So let's just start parsing out group 1 family. Alkali. These are highly reactive. In fact, we kind of consider them to be the most reactive metals. Highly reactive. We consider them to be the most reactive metals. Here's why. They want to lose one valence. You don't know what that word means yet, but it'll matter in a second. One valence electron. And I'll put valence in parentheses because right now that doesn't make any sense to you. One valence electron to become like the noble gas behind it. So lithium really wants to become like helium from an electron standpoint, from an electron counting standpoint. Lithium wants to become like helium, real bad. Now, do we ever mess with proton number? No. So for lithium to stay lithium, we don't mess with the proton numbers, but we can mess with the electrons. It's called taking on a charge. So what we say is alkaline metals always take on a 1+ charge when bonding. Okay. And of course it's a metal. So all those things that we've talked about metals in general apply to it still. Right? Now we're just getting into another layer of specificity. Another layer. Group 2, alkaline. And here's a little trick, by the way, to remember. Alkali is the first column, alkaline is the second. Alkali is a shorter word, it comes first. Alkaline is a longer word, it comes second. Okay. So reactivity, it is also reactive. Okay, but not as much as alkali. It also wants to lose valence electrons. But it doesn't want to lose one. Now it wants to lose 2 valence electrons. And again, that word valence will become very important in a little bit. Right, my TAs?
I love valence electrons.
We love valence electrons. Valence electrons make the world go round, folks. Okay?
Hell yeah, they do.
Heck yeah. For all the parents. Heck yeah. Okay. I don't know. I've already made so many funny jokes on them. So want to lose 2 valence electrons. And so this is why it's a little harder to react with, actually, because try getting 2 people to buy from you, not just one, right? Try getting 2 atoms to want both of your electrons, not just one. Easy to kind of sell off one thing, be like, okay, then, okay, now you have a whole set. You got to look for a specific buyer. You got to look for somebody else that wants them, right? And that's a little harder. So they're not as easily to react. They don't have as easy as an exchange to find, a partner to exchange with, okay? And they do this just like the alkali. They do it to become like the noble gas behind it. But that noble gas is now 2 seats away, 2 slots away, 2 boxes away from it, right? Become like the noble gas behind it. Again, not proton count wise, all electron count wise. We're only changing electrons here. We're taking on what we say, always take on what type of charge? What's going to be our charge for this family of elements when bonding? 2+. They always take on a 2+ charge when bonding. Right? Something else about alkaline is that they actually tend to be denser, like physically denser than alkali. That's just from a general standpoint of view, denser. Okay, halogens. Okay, reactivity wise, they're the most reactive of the nonmetals. Okay, most reactive of the nonmetals. Can anyone tell me why? Can anyone make a guess based off the pattern that you're observing from the previous? What do they really want? They just really want to gain one electron. So they're just as desperate as an alkali, just the opposite way. One really wants to lose one to become like the noble gas behind it. But this group of family really wants to gain one to become like the noble gas in front of it. Okay, so what are they going to do? They want to gain, okay, gain one valence. Electron, okay, to become like the noble gas in front of it. So what are they going to do? They're always going to take on what charge? A 1 minus. Seeing the patterns? Are we starting to see that this is not just any old table, folks? This is not just a list of all the elements out there. This is a predictive bonding table. We can actually make conclusions and predict the future of how two chemicals that we never combined together are probably going to do, what they're probably going to do, what they're probably going to create, right? If it's going to kill us, all right? Always takes on a 1 minus charge when bonding. All right. From a physical standpoint, these tend to be gases, right? Halogens are usually gas. Okay. And don't forget, they also like to bond to themselves. Don't forget that thing. I forgot to highlight this a little earlier, so I'm going to quickly go up to noble gases again. One last thing about noble gases is we say that they're special because they usually are non-reactive. They don't really need to react with anybody to achieve anything, usually. Noble gases, going back to the previous page, I forgot to mention that they're usually non-reactive, partly because everyone wants to be like them. They don't really need to make a deal. If you're the best of the best already, you don't really have to make deals with the lowly, right? The peasants of the elemental world. Yes.
What does it mean, like in front of it or behind it?
And physically on the periodic table, they want to be like the noble gas in front of it. Fluorine wants to be like neon, but lithium wants to be like helium. So it goes row 1, row 2, row 3, like an orchestra, right? You build out the seats. Okay. So that's where I'm going to stop for today, note-wise. For those of you at home, we're doing a physical activity in class, but you should definitely look at the how to color in your periodic table video and start getting some of that information on paper, visualized, color coordinated for you to learn and remember, because on tests, you will be given a blank periodic table. So start now by creating color-coded systems to figure out all the information. The how to color in the periodic table is linked on my agenda, and it's on my YouTube, and it's on my website. Good luck. Bye.